All right, let's go on a little journey. We're about to look at the world in a way that might just change how you see, well, everything. And it all starts with something we all learned about in school, the atom. But that simple picture you have in your head, it's hiding a really surprising and mostly empty truth. You've seen this, right? A picture like this has probably been in every science textbook you've ever opened. It's that classic solar system model. You've got the nucleus in the middle, and then these little electrons are just zipping around it in these perfect little orbits. It's nice, it's neat, and you know what? It makes sense. But what if I told you that simple, tidy picture is, well, it's wrong? Not just a little bit wrong, but almost completely wrong. The reality is so much weirder, so much emptier, and honestly, 1,000 times more fascinating than you can even imagine. So, how did we figure this out? Well, to get to the truth of the atom, we have to jump back in time to a game changing experiment from the early 1900s. It was led by a physicist named Ernest Rutherford, and he basically decided to just poke an atom and see what was really inside. The whole setup, it was actually pretty simple, but totally brilliant. He took these microscopic bullets, they're called alpha particles, and he fired them at a target. The target was a sheet of gold foil that was so thin it was practically see-through, just a few atoms thick. Then, all he had to do was watch where the bullets went. Now, based on the old model, everyone expected those particles to just blast right through, like shooting a BB gun through a piece of tissue paper. And most of them did. But what they saw next was just jaw-dropping. Some of the particles got knocked off course, and, get this, a very tiny number, about 1 in every 8,000, hit something and bounced almost straight back. Rutherford himself said it was as unbelievable as if you fired a cannonball at a piece of tissue paper and it came back and hit you. There was only one possible explanation for this. The atom wasn't a solid little blob. It had to be almost entirely empty space with nearly all its mass packed into an unbelievably small, dense core at the center, what we now call the nucleus. So this was a massive discovery. Problem solved, right? Well, not exactly. In fact, this new nuclear atom created a brand new problem, a huge one, that basically threatened to break physics as they knew it. You see, according to the laws of physics at the time, what we call classical physics, any little charged particle that's moving in a circle, like an electron supposedly orbiting the nucleus, has to be giving off energy. It has to, which means it should lose speed, spiral inward, and just crash into the nucleus in like a fraction of a second. If those old rules were right, atoms couldn't exist for more than a blink of an eye. The chair you're sitting on, this screen, none of it should be stable. Everything should have just collapsed in a puff of energy the moment the universe began. So what was going on? The old physics was broken. The clue that solved this whole mess came from a completely wild idea from a physicist named Louis de Broglie. He said, hey, what if these things like electrons, what if they aren't just little balls? What if they're also waves? And he didn't mean it's like a wave. He meant an electron fundamentally is a wave, something that's smeared out through space. And that one idea, this concept of wave-particle duality, it changed everything. It was the key that unlocked the true secret of the atom. It didn't just update the old model, it tossed it right out the window and started from scratch with a brand new science, quantum mechanics. Now, to be clear, the chemists had the right list of ingredients. They knew that atoms were made of electrons, protons, and neutrons. That idea worked perfectly to explain all the reactions. The problem wasn't what was in the atom, it was all about how those parts were behaving. This new, bizarre reality meant that the old physics was out. The rules that worked for things like baseballs and planets were totally useless for the tiny world of the atom. We needed a new rulebook, and that rulebook was quantum mechanics. So forget about those neat little orbits. In the quantum world, an electron doesn't follow a path at all. Instead, it exists in something called an orbital, which is basically just a cloud of probability. It's kind of like a beehive. You never know exactly where any single bee is, but you know the swarm exists in this general 3D shape. That's the orbital. And these clouds have specific shapes, like spheres or dumbbells, and they have different energy levels. Okay, so we have these weird probability clouds. How in the world do you build, everything out of that? Well, it turns out these quantum rules aren't random at all. They're like a precise blueprint for building every single element in the universe. There's a rule for this called the Aufbau principle. And honestly, it's pretty simple. Electrons are lazy, they always want to be in the lowest energy spot they can find. So, to build an atom, you just start at the bottom, fill up the lowest energy orbital with electrons, then move to the next one up, and so on. You just keep filling them up from the bottom. And here is where it all clicks together so beautifully. That periodic table you remember from chemistry class, it's not just some random chart. Its entire structure, every row, every block, is a perfect, direct map of how these quantum electron orbitals are filled. It's amazing.
All right, so we've gone from a simple solar system to this bizarre quantum world of probability clouds. But let's get back to the real world. How does all this abstract stuff make the chair you're sitting on actually feel solid?
The entire secret, the key to everything, comes down to the very specific shapes of those electron orbitals we were just talking about. The geometry of those fuzzy clouds is one of the most important things in all of science. Because when two atoms get close enough to each other, their electron clouds can actually overlap. They can merge and share their electrons. And that sharing, right there, in that overlapping region of probability, that is a chemical bond. It's the fundamental glue that holds all matter together. And that's kinda it. From the simplest molecule of water to the incredibly complex strand of DNA that makes you who you are, every single thing is just the result of these quantum probability clouds overlapping in just the right way. Our solid world is literally built on a foundation of quantum emptiness. Which brings us to one last, kind of mind-bending thought. The next time you tap your finger on a desk, just remember, you're not actually touching a solid thing. What you feel is just the repulsion force between the electron clouds in your atoms and the electron clouds in the desk's atoms. So if everything around you and everything in you is just mostly empty space, held together by these strange rules of probability, what does that really make you?